Hey y'all, it's Miss Perkins again. I'm going to go through the formula chart that I want y'all to use for your quiz assignments that are coming up. And this is in relation to our electric power notes. Okay, so whenever we first started our notes, we started off by talking about electric power. Okay, and we did have a nice little triangle for that. And in that triangle, we had that power is equal to current times your voltage. Okay, and what we like about these triangles is that they allow us to rearrange without having to really do algebra. So, for example, if they are across from each other, like so, you're multiplying. Okay, whereas if they are one on top of the other, like so, you divide. Okay, so what we end up with is that power is equal to current times voltage. Current is equal to power divided by voltage. And voltage is equal to power divided by current. All right, so what do you think? I think the next thing that we talked about, so okay, also power, our unit, is watts. Okay, I feel like there was something else. Oh, it was energy. Okay, our units for energy, specifically electrical energy, our units are kilowatt hours. And remember, whenever we're converting from watts to kilowatts, we're going from something smaller to something bigger. So let's say you have 100 watts. All right, this is an example. And you want to convert to kilowatts. Okay, so whenever you do your dimensional analysis, right now we have our watts, basically 100 watts over 1. And we want our watts to cancel, and we want to end up with kilowatts before we move on to the next step, which is kilowatt hour, to get kilowatt hours. So we need to divide by watts. Okay. So some amount of watts per kilowatt. Okay, and since kilowatts are bigger, we say that the smaller thing ends up being equal to 1 kilowatt. Okay, and we can know how many because of Kiss Her Daily, because divorce costs millions. So we have watts, which is our base unit, and we want to end up at the kilo. Okay, so 1, 2, 3 times we move our decimal to the left, which is the same as dividing by 1,000. Okay, which is what we end up doing here. All right, and so I end up getting 100 watts divided by 1,000 is equal to 0.1 kilowatts. And then finally, to get kilowatt hours, how we solve for electrical energy is we multiply our power in kilowatts times our time in hours. Okay, so let's say I have 10 hours. All right, so then I end up with 1 kilowatt hour. Okay, so that was power and electrical energy. So I'm going to label specifically what I want the formulas in your notes to be, and you're more than welcome to draw your triangles too. Okay, so this is my first formula. I'm going to highlight it. Okay, and also I would like y'all to include the triangle in your notes or your formula charts, depending on what assignment you're doing, because I do want y'all to have those for your quizzes. Okay, for electrical energy, this is the formula that we're looking at. Okay, so that's your first two. The next set of notes that I want us to think about and recall are our Ohm's Law notes. So I'm going to separate these. All right, so pulling from the Ohm's Law notes. And basically Ohm's Law is voltage is equal to current times resistance. The new variable here is resistance. All right, so we do have another glorious triangle. Okay. Our voltage is equal to current times resistance. And of course, if they're one on top of the other, you divide. Okay, so we can derive our other two equations besides V is equal to I times R from this triangle. So we have voltage is equal to current times resistance. The units for voltage are volts. The unit for current is amperes or amps. And finally, the unit for resistance is ohms. And specifically, we use the omega symbol. Okay, so we got V is equal to I times R. And from using our triangle, we can also derive that current is equal to voltage divided by resistance. And resistance is equal to voltage divided by current, right? So from Ohm's Law notes, these three are also important, okay? So those will be your next, I guess, three equations that you're gonna need. Probably not one, I guess we're gonna call that one 3, 4, and 5. Okay, oops, my pencil slipped. All right, let's see. So we had electric power, Ohm's Law, and then finally, the last one, if you can believe it, that we really talked about was our formulas that had to do with finding the total resistance in our circuits. Okay, so for this one, let's just play with the sparkly color because I'm bored and it's 11 at night, so yeah, this is when I get all my work done now. All right, so I'm going to start off talking about calculating total resistance. This looks like a Cheeto. Total resistance, and this is going to be in a series circuit. All right, so my total resistance we abbreviate with RT. That's equal to the sum of all the resistors in that circuit. And so on. All right, so that one's super easy, super easy. Just add your resistances together, and if you forget which ones are your resistances because they're not specifically labeled that way, you'll know because they have the omega symbol for their unit ohms. And then for a parallel circuit, to find your total resistance, you actually have to take the reciprocal of all of your individual resistances. Okay, so you have 1 over R1 plus 1 over R2 plus 1 over R3, and so on. All right, so then remember, if you have numbers that are not easy to find your common denominator, you multiply your denominators. All right, so what I'm going to do is I'm going to do 2 different examples of that, just so that way you have it in your head about like how to do both ways. Okay, so let's say for example number 1, my resistances are, let's not use crazy numbers. Let's go 2 ohms. R2, let's say, is 6 ohms. And R3, let's make it 12 ohms. Okay? So if I have these in parallel, it's gonna take a second to draw my resistor, or sorry, my circuit with my resistors flowing through it. All right, so this one's R1, R2, and R3. This is my battery. Remember, the smaller side is your negative terminal. The larger side of the battery is the positive terminal, on the drawing anyways. And so your current flows that way. Just to remind you all, remember we always flow from anode to cathode, negative terminal to positive terminal, all right? So since we're in parallel, to find our total resistance, we reciprocate all of our resistances. Right? And that is ohms. Sorry, it's ugly. Okay. So if we think about what number every single one of these denominators goes into, take a second. 6, does 6 go into 12? Does 2 go into 12? If the answers to your questions are yes, you just had a really easy time finding a common denominator. Okay? So hopefully by now you've figured out your common denominator here is 12. All right, so we make all of our common denominators 12 ohms. And we figure out what we have to do to the numerators now based on how we get the denominator to be 12. So let's see if that makes sense in a second. If you don't have to do anything to change 12 into 12, then you keep your numerator the same, okay? So 12 times 1 is 12. 1 times 1 is 1. Okay, for this next part, I'm going from 6 to 12. So I have to multiply by 2. I'm going to do the same with my numerator. 1 times 2 is 2. And then from 2 to 12, I have to multiply by 6. So I'm going to do the same thing to my numerator. All right, and so therefore my numerator is 6. All right? So now I can add my numerators together. 6 plus 2 is 8, plus 1 is 9, over 12 ohms. And now I have to flip my fraction back around. 12 divided by 9. And so now I have my total resistance. And forgive my brain deadiness, but I need to use a calculator to my shame, to my chagrin. 12 divided by 9, it's 1.33. And that is ohms, okay? So that was with an easy common denominator, nothing too crazy. Now let's say in a different example, this time, let's use a nice distracting rainbow color. Okay, this time we're doing example number 2, and that's actually maybe too distracting. Okay, we'll use, options to the point of paralysis, right? So for example 2, we're looking at the same overall circuit outline, but our resistances are what's going to be different this time. All right, so let's say my first one is 63 ohms. My second resistance is maybe 29. And my last one is 104 ohms. Okay, so I don't really care about does this actually work in the circuit or not. I'm just trying to see what my total resistance is going to be in this parallel circuit. So I'm going to set it up the exact same way that I did. 1 over RT is equal to 1 over 63 ohms plus 1 over 29 ohms plus 1 over 104 ohms. And I would rather die than spend my entire day trying to figure out a common denominator for this. So the method that I know is going to work every single time is going to be if I multiply all 3 of these together. Okay, I know this is going to work and it's going to give me a common denominator because if I'm multiplying all these numbers together, all of them can definitely be divisible by the number that you get, or the number that you get is divisible by all of those numbers, okay? Because you had to multiply all of them to get that. All right, so let's see what we end up getting. Let's see this bad boy. 63 times 29 times 104. And I kept the numbers like quote unquote smaller for my own sanity. This is 190,008. That is our common denominator. Love that. And you may be like, Miss Perkins, that sucks. But I promise you it works every time. Okay? All right. And to figure out what the numerators will be, what I do is I take the 190,008 and I divide it by the number that my fraction was originally. I don't know how to make the words right. Okay. So I'm going to divide those. And that makes my numerator 3,016. I'm going to do the same thing for the rest of my numbers. Divided by 29. And divided by 104. So I take some time to use my calculator on my phone. Divide by 29, that gives me 6,552. And then my last one, 190,008 divided by 104. And that gives me 1,827. All right, so brutal, but that's the easiest way I know to take these crazy numbers and make them work for you. So I'm going to erase the part in white at the bottom because I'm done with that now. And I like having space. So now I need to add these up. I'm sorry if you can hear snoring in the background. That's my boyfriend. All right, 6,552, and then plus 3,016, and my total is 11,395, and that is over 190,008. So now I flip. My total resistance is going to be 1,908 divided by 11,395. And I end up getting, I'm going to round to 2 decimals, 16.67 ohms for my total resistance. Okay, so it's really not that crazy. I'm going to outline the steps because, again, this was for our formula chart. It was not meant to be insane and nasty and disgusting, okay? It just wanted it to be thorough. So I'm going to outline the steps. And let's do, why am I having color paralysis? Let's do like this lavendery color. Okay, so the first step is to reciprocate. Step 1, reciprocate your resistances, which basically means put them underneath 1. So therefore, if my resistance is 13 ohms, I make it 1 over 13 ohms. Okay, so that's what we end up doing there. That's what that means, okay? Step 2, find your common denominator. Okay, and your numerators are not going to all stay 1. Once you find your common denominator, some numerators may change, especially if the denominator had to change. But as you saw in my first example, 1 over 12 ended up staying the same. Okay. Sorry, those kind of ugly arrows. Okay. But not all of your numbers will change. It depends on if your denominator had to change. Okay. Step 3, you add your numerators. Step 4, you flip your fraction. And then you divide. So you do not divide first. You have to flip your fraction like we did here to be 12 over 9. Okay, so we flipped it and then we divided to get 1.33. If we had done 9 divided by 12, we would have gotten a very different answer. We would have gotten 0.75. And that is not 1.33. And, you know, like, you could argue that, oh, miss, in the grand scheme of life, they're close. Not close enough. Not close enough at all. Okay? And then once you divide, you've got your answer. Yeah. So that is parallel circuits, but clearly series is much easier based on the fact that that's it. That's all of it. Yeah. Alrighty, well, hopefully that wasn't too overwhelming. I know that kind of took a while, but that's what I want on your formula charts. Okay, I hope that helps. Hope the examples were refreshing.